Share screen too. All right, let's go with the TED.
You probably already know that everything is made up of little tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer is that they are really, really, really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question. How many atoms are in a grapefruit? Well, let's assume that the grapefruit is made up of only nitrogen atoms, which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry. And then how big would the grapefruit have to be? It would have to be the same size of, actually, the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit? That's right. So how big's the atom? That's really, 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 really small. And you know what? It gets even more crazy. Let's now look inside of each atom. That's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom, the blueberry, to the size of a house. So imagine a ball that is as tall as a two-story house. Let's look for the nucleus in the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium. So imagine a ball the size of a football stadium. And right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble. And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium with the nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit. Okay, one more thing, if I can even get more bizarre. Since virtually all of the mass of an atom is in the nucleus, now there is some amount of mass in the electrons, but most of it is in the nucleus. How dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cube. But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet. Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot. And let's go and grab all of the nuclei from a typical car. Now, cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of a nucleus? Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth.
Ooh. Crazy big. Over here. Okay, so a couple other things to wrap up there with, but here's some things I got. So if you're trying to visualize like how small are we talking about? Because quantum mechanics, we're talking about like this scale, right? So this size, and the laws of physics, well, they work a bit different down there, right? So things have this weird wave particle duality. Things can both have properties of particles and waves at the same time. Particles exist probabilistically, right? So if you're trying to figure out like exactly where something, how fast it's moving, well, it's kind of a numbers game. That's why I started this with a statistics packet. So you have some probability curves in your mind. So it's a good framework to work with. And so, but yeah, what's the scale we're talking about here? So an atom to grapefruit, well, that's kind of analogous in size blueberry to like the size of the entire Earth. Well, you said a nitrogen atom, but so you guys get the idea. Ooh, all right, so yeah, that's a good mental model for like the size we're talking about. And the structure of the atom, well, most of the mass is in the nucleus, right? So that's protons and neutrons. Now electrons have a tiny bit of mass, but really small compared to the nucleus, the protons and neutrons. Okay. And most of the atom is empty space. So what's going on with the nucleus? Well, the nucleus compared to the size of the whole atom, it's kind of like a marble compared to the entire stadium. Right? And that's where almost all that mass is. So the density of a nucleus, well, it'd be kind of like if you took 6 billion cars, 6.2 billion, so round a little bit, 6 billion cars and put them in a 1 cubic foot box. Ooh, right now we're talking about the density of a nucleus. Right? And remember, this makes up, this all the matter in the room is just made up out of atoms. But, okay, so really dense nucleus, most empty space. There you go. All right. Next part is journey. Doing this kind of chronologically. So now we got the idea of scale that we're talking about. Let's flip over and look at photoelectric effect. Now to introduce this a bit while you guys are wrapping up these notes is it was a question for a long time in physics. What is light fundamentally? Is light fundamentally made of particles or is it waves, right? And particles have certain properties, right? They have mass and velocity and little balls of matter. And waves have certain properties, right? So if you put a wave through, say a slit, it'll go through its diffraction. If you put it through 2 slits, it'll create an interference pattern, like properties of waves. Well, by about the end of the 19th century or so, it had kind of been settled that, okay, light is made of waves. Okay, great. Classical physics, light's waves, good. Call it a day. Right? But if you collect light energy on a photovoltaic cell, it does something kind of funny that no one could quite explain. So here, let's flip my screen back over. I'll take you guys through the story and we'll draw a graph and look into this photoelectric effect.
So let's talk about the photoelectric effect. The photoelectric effect is a very, very, very important effect that was discovered by Heinrich Hertz in 1887, who was incidentally the first guy that made electromagnetic waves and was able to demonstrate their existence. It was during this study of electromagnetic waves that he saw that if you send ultraviolet light onto metals, you'll get sparks coming off. Now, he didn't really know what it was, but he was the first one to see that effect. Now, later on, it was explained by Albert Einstein in 1905. He actually won the Nobel Prize in Physics for that explanation later on. This explanation actually cemented the place that photons have in the development of quantum mechanics, because the photoelectric effect was one of the first direct observations of photons that can even be pointed to. All right, so what is the photoelectric effect? Well, essentially what we're going to do is we're going to take a freshly cut piece of metal and put it in a vacuum. And then we're going to shine light on it. Now, sometimes this light will cause electrons to jump off of the metal. All right. Now, classically, we would expect, light's a wave, right? So if you pump up the intensity, then you ought to get more electrons, right? So regardless of what the metal is, if I shine a 300-watt laser on it, I ought to get some electrons jumping off. So that's what I expect. The observation is that that's not what happens, all right? The observation is that if I have some frequencies, yes, increasing the intensity will increase the number of electrons. But if I try to go below a certain frequency, I don't get any electrons at all. Doesn't matter what the intensity is. Doesn't matter. And it's a sharp cutoff. Get electrons? No electrons. All right? So this was not understood at all. Now, the experimental setup is important to understand. What we're doing is we've got a vacuum chamber in here. We've got a circuit that we're driving by a battery. Now, this is all vacuum. Nobody can get across without an impetus to do so. The electrons, however, would desperately like to be on this side because that's the positive side. Remember, the long side is the positive side of the battery. So the electrons really do want to jump across. So what we do is we then shine our light. Now, if an electron is liberated, it's going to jump across, definitely.
All right. So we're shining a light so the electron could jump across. You're thinking, suppose you shine a light, it's like, okay, well, it's not enough energy. Hey, do you think a good idea might be just to turn up the intensity, like make the light brighter? That might give it more energy, right? And if you think in like a classical physics sense, that was the operating hypothesis. Right? And that's what this guy, Heinrich Hertz, was doing back in 1887. But there was a problem, which was that that did not produce the expected effect. Right? So here's a graph. This graph I'm gonna have you guys draw too, but let's look at this first. So here's some actual experimental data. Now this was, I think we should, this is from 1916, but Heinrich Hertz did basically the same experiment back in 1887 and found that below this threshold, right, here's the frequency of light. The corresponding wavelength is like 683 nanometers, but right, so like this many hertz frequency. If it's below that frequency, it didn't matter how bright the light was shining, you wouldn't get anything at all. And if it was above that frequency, now there was this direct relationship where increasing the frequency, like if you double the frequency above that threshold frequency, then you could also double the amount of energy that you got. You guys see increasing frequency to the right and increasing energy going up. Right? Most of the time in this class, we measure energy in joules, but here's doing electron volts. Electron volt is a tiny, tiny unit of energy. Right, so switch my screen over. Oh, oops. Sorry guys, if you're at home, let me show you guys that graph. All right, so there you go. If you're at home, you can see graph I was just referring to. All right, you guys in class. Right, there you go. There's some notes I got marked up. All right, so Heinrich Hertz's experiment back at the end of the 19th century. And again, according to classical physics, like, okay, well, something's amiss. We can't quite put the story together. Albert Einstein comes along in 1905. This is Albert Einstein's miracle year. This is the same year he also publishes on special relativity. Okay? And he actually explains this photoelectric effect with what I'm going to go into the next quadrant by saying, you know what, light, which we kind of thought we determined to be a wave by this point in physics history, actually it has this duality, and it also has this property, or this particle property too. And for explaining this photoelectric effect, this is what Einstein actually got the Nobel Prize in Physics for. Like weirdly enough, he never actually got the Nobel Prize in Physics for relativity, which you would think, because that's what he's most known for. But no, he actually got for this right here, explaining this photoelectric effect. And the slope of this line, right, the relationship between energy and frequency, it has a name, and it also has a character. I'm going to call H, and that's Planck's constant. Or maybe sometimes you hear like Planck's constant, say Planck, because yeah, say it like an American. There you go. Planck's constant, Planck's constant, one or the other. Wonderful. Okay, and here, actually, just go ahead straight to this next quadrant right here. So I'll show you guys what Planck's constant is. It's a very tiny, tiny, tiny number. So it's like 6.626 times 10 to the negative 34 joule seconds. Okay. Do you guys remember, I meant to mention, this is a universal constant in nature. Do you guys remember, for example, universal gravitation? There was capital G was 6.67 times 10 to the negative 11 meters squared per kilogram squared. You guys remember that? So that was another one of these universal constants. So is the speed of light, 3 times 10 to the 8 meters per second, right? So nobody knows why these numbers are what they are, but they've just been measured to be these things. Right? And actually, a lot of our modern, say, definitions of what is a kilogram, what is a meter, what is a second, scientists have been able to, by this point in history, and only very recently, in the case of math, been able to tie all these definitions back to fundamental constants and universal constants. Okay, but what's the deal here with Einstein's explanation of this photoelectric effect. So I want to give you guys a garden hose model. Let's look at a garden hose model. So I'm going to draw a couple of garden hoses. Okay. So call this the garden hose model. Okay. One of these I'll have a low frequency light. The other one will have high frequency light. Okay. So think of these, maybe just like, say these are shining lights on, say, a PV cell, right? We're trying to collect light energy. Oh, finish this out. Right. So if you saw a low frequency wavelength of light, do you think that might look something? Okay, so just draw a wave in here, right? Something like that. Right. Versus if you saw high frequency, do you think it would probably look more like this? Okay, so low frequency, long wavelength, high frequency, short wavelength. Okay. And if we're talking about visible light, then low frequency might be like red light, and high frequency might be blue light, for example. Right. But of course, you could go lower frequency than red light. That would just go to infrared and then microwaves and radio waves. You could go higher frequency than blue or violet. That would go into ultraviolet and then X-rays and gamma rays. Right? Why is it that, say, the low frequency might produce nothing at all? That's like this part of the graph. Right? There's no energy at all. Right? But the high frequency actually does. And then once you say like double the frequency past this threshold, then you could like double the energy. Okay? So here's what, no, of course, that threshold is like the minimum you need to get the electrons to jump at all. But then after that, you can gather the energy and like use it, right? Like the energy. Okay? So Einstein says, actually, let's go back to a particle model for light. And I'm going to call these particles photons. Each one of these, maybe we'll put it every single crest and trough. I'm just drawing a photon. That's what this is right here, right? A photon. Right? And that could be, a packet of light energy, right? And here's what it looks like for high frequency. Ooh, okay. So I have a bunch of marbles running through these two garden hoses. Here's what low frequency is going through a garden hose. The marbles still coming out like this, like bump, 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 bump. Here's high frequency marbles going through garden hose. Ooh, and every single one of those marbles represents like a packet of energy. That's why, like, if you double the frequency, you're gonna double the number of marbles per unit time, like you're doubling the amount of energy that you're gathering, which exactly explains why this graph is a direct relationship. Yeah, you guys see it, but light's linear. Okay. Oh, no, okay, no, we're good. We got a little spare time in here. I'm going a little slower with this class because, yeah, I know we've got a little bit more time than most of our class. We've got half an hour till lunch. So here's what we do. We're going to do one more of these quadrants because I want to keep my classes basically on track with each other. So we're going to look at what is meant by Planck time and Planck length. And then we'll hit a pause point for today. Right? So we flip the screen back over. I got a couple of short clips. And then I'll give you guys the notes on those. All right, let's start with say Planck length.
What is the smallest distance you can think of? If you're thinking of something like the width of an atom or electron, then you are way off the mark. There is a distance so unimaginably small that it makes distances comparable to an atom seem giant. This distance is referred to as the Planck length. The Planck length is roughly 1.616 times 10 to the negative 35th meters long. However, numbers to such an extreme value such as this are very difficult to comprehend. So let's put it into perspective. The approximate smallest distance an unaided human eye can observe is about 0.1 millimeters. This is about the width of a single human hair. Now, imagine expanding this distance to the size of the observable universe. How big would a Planck length be? Coincidentally, a Planck length would now be 0.1 millimeters long. In other words, the width of a human hair is just as close in size to the observable universe than it is to a Planck length. The question that arises here is, why is that the smallest distance? Why can't we take measurements that deal with half a Planck length or a quarter of a Planck length? Although this concept works out well in mathematics, in the real world, things are much trickier. At the Planck length, ordinary space and time cease to exist. There's possibly just nothing in between two individual Planck lengths. Time on this level just skips across Planck lengths, leaving nothing in between. Distances conceived as smaller than the Planck length inevitably boil down to the realm of quantum mechanics. Because quantum gravity dominates here, it becomes impossible to determine the difference between two locations less than a Planck length apart. Thank you for watching this episode. If you enjoyed it, please feel free to leave a like.
Scientists think it took less than a millionth of a millionth of a millionth of a millionth of a second for the universe to expand from the size of an atom to a baseball. That may not sound like much, but it's like a golf ball expanding to the size of the Earth in the same amount of time. That means it was expanding faster than the speed of light. That's fast.
So many things were happening so fast in the early universe because everything was so close together that we need a new unit of time to describe things.
It's called Planck time. To understand just how short a Planck time is, consider this. There are more units of Planck time in 1 second than all the seconds since the Big Bang. The math is mind-blowing. There are more than 31 million seconds in a year, and it's been 14 billion years since the Big Bang. So multiply 31,556,926 by 14 billion, and what you get is a really big number.
It's a time scale that's so small that all human intuition goes out the window. If we look at our watches and measure 1 second, we can ask how many Planck times is that? Well, it is a billion, 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 billion Planck times.
All right. So those were real short. Show you what things I got out of those, or some details I can fit in here. All right. So you guys know, like, if you look at a computer screen or your phone screen and you see an image, or maybe there's a video playing, or you see the video running, and it looks fluid, right? It looks fluid, continuous, but you know, if you look close enough to the screen, if you get down small enough, that, well, it's really all pixelated, right? It's just made a bunch of blinking lights and pixels. Is the universe kind of like that? Like, can you subdivide forever? Can you split this in half and half and half, and eventually you get down to atoms, and then maybe you can split those in half and half and half and keep going, right? Well, no, the universe sort of actually is pixelated, right? There's the smallest meaningful unit of time, and there's the smallest meaningful distance where it doesn't really make any sense to subdivide it. Now, I can't tell you why it's the case, but this is what quantum physicists say. So we'll run with that. But I think if you do this many meters divided by this many seconds, you get the speed of light. So that might be related to it. But yeah, here you go. So now, right at the tail end of that last video where you're talking about how long is a Planck time, you're saying that there would be more Planck time in 1 second than all the seconds in the since the Big Bang of the universe, and it's not even close, because if you go with the numbers, you're saying it'd be like billion, billions, right? The universe is only 14 billion years old, so that's like, order of magnitude of about 10 billion. So if you're trying to billions of billions of billions of Planck time at every second, ooh, man. So because billion is 10 to the 9, right? You're trying, like, it would take like 10 to the 44 Planck time just to get up to a second. So yeah, it's a great small unit of time. And then Planck length, the smallest meaningful length in the universe. Okay, so I think this is the first one I played for you guys. So if you look at the Planck length compared to the width of, say, like your hair, right, width of a human hair, right? That is the same proportion as the width of your hair to the diameter of the observable universe. So crazy small length going on there, but yeah, we try to get it physically smaller, and it'll make a lot of sense. All right, so that will be our pause point today. Yeah, so I'm gonna close out this Zoom recording.